In the following lesson, we will discuss the available approaches for using source code with the extension development approach. A similar code extension mechanism already exists for X++ and is modeled after the corresponding feature in C#. Under this mechanism, a class can be designated as an extension class through a naming convention and by hosting public static methods. In this existing feature, the type of the first augment that is passed to the extension method is the type toExtend. What this module describes is the next step in that direction, which offers a more capable and natural extension story. In object-oriented programming, the term extend has a well-defined meaning. If we say class B extends class A, we mean that it inherits from class A and the usual object-oriented rules are implied. In fact, this term is even used in the X++ syntax that is used in class declarations to express this relationship. At the same time, we use the term extension to talk about metadata that has contributions from several models. To avoid overloading the term extend, we will instead use the term class augmentation to designate the relationship between class A in the base model and class B in the model that depends on it, where B provides additional functionality to class A in the context of that model. Nevertheless, we will also continue to use the term extension class because it is prevalent. So as you can see, we have a parent class and we have the extended class, which we could also call the child class. So here parent class has methods A and B, and then we've extended it to include both methods A and B, and we've added a method C to this extended class or child class. When we are developing code in our new extension model and package, we can always create new elements, such as a new class. Remember, we must create references to the models that contain the elements we wish to reference in our code. If we do not reference the application suite, for example, we will not be able to reference invent cost trans cost list class. So here we have our new model and we are going to be extending the invent cost trans cost list. We must reference the application suite in our new model when we are creating it, or we can update parameters in Visual Studio to do so from the Dynamics 365 menu. It is useful to have a term for class that consists of the public members of the augmented artifact and all the public members of all the class extensions that augment that artifact. This class is called the effective class in a given model. The following illustration shows an artifact which is called myArtifact, as we can see here over on the left-hand side. This is defined in the base model called myModel, and it's dependent on two models that have extension classes for myArtifact. So here we have our two extension classes of my2 extension and another extension, which are in two different models of another model and my extension model. So in this example, the effective class is the class in the extension models that contains all the original methods and all the public artifacts from the extension classes. The effective class isn't the same in every model because it includes only the class extensions that are defined in a given model. This illustration shows the effective class of myArtifact in the myExtension model. Here we can see the effective class concept. We can add new methods and state to my class by introducing an extension class on the extension model, which would be my extension model, that builds on top of, that is, has a dependency on, my model. Extension classes are that are adorned with the extension of attribute, as we can see here in our class. They also have the name of the underscore extension suffix. This restriction on naming might be removed later, but it is important to know that when you are doing a class extension, you have to have this underscore extension suffix, or else you will get a compile error. Because classes are instantiated by the runtime system, it is not meaningful to derive from the extension class. Therefore, the extension class must also be marked as final, as you can see here. The class str compile time function must be used, and it has two uses. So we have this extension of and then class string here. It produces a compilation error if the my class does not exist, and the compile time function that is used tells the compiler what kind of artifact is augmented. So artifact names by themselves don't uniquely identify a given artifact to augment. So for example, forms can have the same names as tables, classes, and enums. So you might have, class table, class string, class. So here we have a class string. Any number of extension classes can augment a given artifact in a particular model. Extension classes are never referenced directly by the programmer, only by the runtime system. It's also important to note that any class that inherits from the augmented class also inherits the effective class. In other words, the classes that inherit from a class that has extensions inherit the methods that are defined in the extension class. We have two different types of constructors, instance and static constructors. The instance constructor is the method that is named new. The instance constructor that is defined in an extension class can't have parameters. Instances of the extension classes are created, and then the runtime system calls their constructors as required by the usage scenario. These constructors are never explicitly called by your code. Constructors are useful for initializing the state of the extension objects. It's guaranteed that the constructor that is provided in the extension class will be called one time before any instance method or the instance state on the extension class is assessed. However, there is no such references made. If there are no references made, the constructor is not called. Next, we have the static constructors. These are the parameterless static methods that are named type new. Static constructors can be defined on extension classes. It is guaranteed that the runtime system will call the constructor before the first reference to the extension type. You cannot assume any particular order of invocation for static construction among a set of extensions. The public methods that are defined in extension classes provide additional functionality to the augmented class in the context of the model where the extension class is defined. Only public methods are exposed in this way. You can define private methods to help implement the public methods, but those private methods aren't part of the effective class. Because extension classes are final methods, these can't be marked as protected. This defines an extension method that is named extension method. And it augments my class. So here we can see we have our extension of, and then we have a class string of my class. And this is our extension method that we have created. So again, the public instance method extension model is defined in the extension class, so therefore it's available just as if it were defined in my class in the context of the model where the extension class is defined. So this following example shows how to call the method in the model. Let's now take a look at a static method. Methods that are defined as public and static in the extension class are available as static methods on the artifact that is augmented. So this following example shows how to call the method in the model. It's important to note that a static method can access the public static methods and state in the effective class of the augmented artifact. As an interesting side effect of this, static extension methods on the global class become available in the language's functions, which are available without any prefix. Now we'll take a look at adding an instance method. Instance state, which is the state that pertains to a particular instance of an artifact, can be specified on extension classes. This example defines a state that is named state. So here we have our extension of and the my class, and we're declaring that as final. And then here we have our public int state and private void new method. A static state applies to the type instead of an instance of the type. In this example, this shows a static extension state. So again, we have our extension of and final, and then we have our public int state public static and static state, and then we have our static void type new method. Let's now review comparison to overlaying in development for Dynamics 365 for finance and operations. Overlaying or overlayering is when you modify existing code by changing the system behavior. Extensions are much more flexible, and they allow you to leave the system behavior in place while adding extra logic around it. Overlaying may seem like a quicker solution, but it comes at the cost of upgrades, hotfixes, maintaining code, and merging code. We'll consider this diagram. We see on the left that overlaying stores customizations in the same assembly or DLL file. In contrast, the extension approach depicted on the right shows that each customization is stored in a separate assembly file with separate extension elements. The ISV1 and ISV2 changes extend elements from the application suite and are stored in separate DLL files. Then, the var extension stores customizations in elements that are extension of ISV1 and ISV2 elements. This creates extension customizations in separate packages and does not affect the standard application at all, making a complete compile of all objects unnecessary. Let's take a further look at overlaying. Overlaying must be referenced to as customizations, or they may be referenced to as customizations. When we use the overlaying approach, we are storing our changes against a particular element in a higher layer. However, it is within the same package and therefore the same assembly. The granularity for overlaying is down the property level. Delta files or XML files for the customized elements store only the changes or customization along with the original value. It's also important to note that when using the extension approach, the purpose of layers changes. With the extension approach, models technically overlayer each other now. Oftentimes, we need to modify system code in the middle of a method or access elements and logic in a higher model from a lower model. In these cases, we would depend on delegates to allow us to implement the necessary logic when developing with extensions. Let's take a further look at delegates and model splits. Delegates allow us to access elements in higher models from a lower model. With the model split, a hierarchy has been created where a higher model can take dependencies and access elements in models below, but not in the models above. In this setup, the application suite has full access to elements in the application foundation and the application platform. Application foundation can access its own elements and those of the application platform. Finally, application platform can only access its own elements. We are also assuming we have created a custom model called test, which can access all models below. While the model split provides many benefits, it creates a problem when trying to access elements defined in higher models. Delegates are the recommended method for accessing elements in higher models from a lower model. Delegates are very similar to events in that we have a delegate instance that is invoked, a handler with compatible signature code is executed. This permits higher layer code, the handler, to be called by a lower layer code, the delegate instance. A delegate declaration must have three main things. It must have the delegate keyword, the type void, and an empty method. Delegate methods serve as means for defining a contract between the delegate instance and the delegate handler. A delegate takes no action itself. This is enforced by having a void type and having no code in the method. In this demonstration, we're just going to take a look at a delegate, which is the dimension hierarchy delegate. So I'm going to go over to my AOT and we're going to search for a class. So I'm just going to go ahead and type in type, followed by a colon, and then in between two quotes, I'm going to go ahead and type in class. So we're going to tell the search we're looking for a class, and I'm just going to go ahead and type in dimension hierarchy and click enter. Now that didn't narrow it down all the way because we have quite a bit, so I'm just going to type in delegates. And there we are. So I'll just right click on this and we're going to open it in the designer. And then I'm going to go ahead and right click again and we're going to view the code. So here we can see our dimension hierarchy delegate, and in particular, we're going to look here at line 10. So this is the call that we use to get a count structure query by ledger for added elements that exist in a higher layer. So this line 10 here is what's going to be making that call to basically allow us to access this data in a higher layer than we are in.